It is. Yeah, it is. But anyway, we'll see. We'll see how it works out. Okay, so thanks for coming. This is just a paper on school choice and education economics. It's to work with my colleague Thilo Klein, former colleague Thilo Klein, from the Center for European Economic Research. So it's a paper about how we allocate kids to school, and it's a follow-up of my previous work. And I'm going to tell you how do we usually allocate students to schools, and I'm going to tell you why that's wrong, and I'm going to propose a new thing that I'm going to show you is going to work better. But let's see, how do we usually allocate students to schools? So the most common practice in many places is just to do catchment areas or allocate kids to the nearest school, just in terms of geographical distance. And that works relatively well because it reduces commuting time. But in a sense, it's not really fair because if you are from a poor area, you're probably condemned to go to a bad school, which is not ideal. Or particularly, it's also a problem because rich parents can buy their way into better schools. And that's also well known. And here are some news articles showing that many people have suggested to ban catchment areas or to try to replace them because of these problems. Ideally, you would like that perhaps if you are a poor student from a poor area, but you have really good grades, you have the chance to attend a better school rather than just have to go to the one that is closer to you. Similarly, here, an article from The Guardian from a few years ago says that 1 in 4 parents in the UK try to play with the catchment areas, try to move to a better place to secure a good seat in the school for their kids. You talk to Sonali, she's having this problem trying to find where to live so their kid can go to a good school. So that's a common way to do it. But as I said, it's not particularly fair, or it's not particularly desirable because you want that very smart kids have the chance to go to better schools. So there's a few other ways to do it. The second one that I'm going to talk about today, well, not really, but just to mention it, is decentralized applications. So think that every school is private, everybody can apply everywhere. Every school has their own admission criteria, and that everybody can decide to accept as many students as they want. That, in a sense, is fair because if you are from a poor area, you can apply to as many schools as you want, and you have a chance. So it's potentially merit-based because every school can determine their admission criteria. Think of it like applying for a PhD. You can apply to as many PhDs as you want. And if you are very good, probably somebody will offer you a place in a top school. However, it also comes with problems, right? So the first problem is that you are applying to many places and probably you will get offers from many places. And probably you're going to wait until the last minute to reject some of these places. And also that conveys a problem that perhaps a student applied to many places but didn't get any offer because those offers have been made to a student that is not going to go anyway. So we can have the case that the student gets a lot of offers and the student doesn't get enough offers. It's also a problem because the admission criteria can be very obscure and can be unfair. It could be based on religion, on race, on socioeconomic status, things we don't want them to be based on. And it's also a problem because it tends to lead to this kind of exploding offers problems in which in a PhD thing, they tell you, you have 3 days to accept or reject this offer. So we think that that's not too good. Decentralized offers have also been used, for example, in China. The students were allocated to schools using decentralized offers, but the enrollment to accepted to enrollment ratio was very low, meaning that a lot of people got offers, but very people show up in the first day. And that partially that was the reason why the Chinese Minister of Education moved to a centralized clearinghouse in which only 1 offer was made to each student. So it's not great. And that's why we've seen that it's not very commonly used for primary schools or secondary schools. Here's another quote. The previous one was from the journal Political Economy, this case of China. For example, you also see that it's documented that in US sometimes this decentralized admission system means that some students, some universities get a very big cohorts, and that conveys problems because they don't have enough housing allocation. They have to set up things last minute. A little bit like Queens this year because too many students were admitted to first years. The university promised that they will be offered a place in the residence halls. The university didn't have enough places. They had to offer vouchers of money for people to not to take this offer of a place where to stay. So it's also problematic. And the third kind of way in which students are assigned to schools, which is the one we're going to be talking about today, is called school choice. It's different in the sense that the students only submit one application to a centralized clearinghouse, and the clearinghouse that tells them where to go. There's only one place to go. So, okay, you said, my favorite school is Queens, then Ulster, then Glasgow, then Warwick, whatever. And yeah, it sounds, yeah, UCAS. Right, and also like the primary school system in England. Yeah, but yeah, it's like actually in the Northern Ireland, they also do something like this. The students rank only submit one application in which they say, this is my favorite primary school, this is my second primary school, third, so. And then the educational authority has all that information, and then sometimes, generally, the educational authority also gets the information from the schools. So this is my top student, this is my second, based on grades, based on centralized scores, interviews, so on and so on. Everywhere in the world they do that, except in Northern Ireland. I found it very curious. In Northern Ireland, all this information about students is sent to the schools, and the schools say, okay, I'm taking this, you handle the rest. So Northern Ireland seems rather cumbersome, but this is very common in the sense of having a centralized clearinghouse in which everybody gets one offer. And this is very popular. Most of the US has school choice, Northern Ireland, Hungary, blah, blah, blah. Benefits, well, there's no certainty of how many people are going to show up. There is no exploding offers. There is a sense of fairness in which everybody can. Where do you go to school is not based on where you live, but where do you want to, in a sense. Your preferences are taken into account. And where does this idea of school choice comes from? All the way from Milton Friedman, who proposed that there should be some sort of competition, not only in the sense that it was good for students, where do I go depends on where do I want to go, but also the public schools, the number of students, it just doesn't come from nowhere. But like, if you are my student, I can choose to go to the top schools, and that forces schools to try to be top, in a sense. And since Milton Friedman proposed this, it has become, by and large, the common way to do admissions, particularly for primary and secondary schools in the US. Right. So as I said, Chris mentions that we have some sort of school choice for universities with UCAS. We also have it in Northern Ireland, in England, school choice. Since 1988, parents can signal where do they want their kids to go. Similarly, in the US, most of states have some measure of school choice. And the literature, by far, there's a consensus that school choice has been good for students. It leads to higher grades, higher wages later. It leads to higher educational attainment. Basically, it's very good. There is some discussion on whether school choice has led to more segregation, and they have been findings on both sides. In some cases it does, in some cases it doesn't. The sense that with school choice, all the top students tend to be of particular race, particular socioeconomic level, particular religion in Northern Ireland, and they are all applying to some schools, and they have the best grades, of course they get in. But I think we can agree that probably still fairer than catchment areas, because it still gives them a chance to very good students. Do you mean like assortative matching? Yeah, of course. Yeah, because better students tend to be correlated to other characteristics. Yeah, there's not really way to get rid of that segregation entirely, but at least it gives them a choice. No, like it's not like in terms of catchment areas in the US that is entirely segregated, or here in terms of religion. If you are in a Catholic area, you go to a Catholic school, or if you are from a Black neighborhood, you go to a Black school. At least, of course, there's still segregation, but I think still gives you a chance to escape it. But yeah, I'm not going to talk about segregation today, but it's a debate. I just want to mention it. As I said, yeah. Mm. Yeah. Yeah, that's true. Yeah, that's true. That's true. But for example, in yeah. Mm. Yeah, you do. And nowadays they have been trying to be quotas. On the data that we're going to use today, for example, in Hungary, the schools report their priorities over students, but they are told like, you come up with a number of how good the student is, but only 15% of that number can be influenced on grades. Only 15 can be influenced on the interviews. So at least there, in some cases, there is more transparency on how, you will see how the data we're going to use. But it's a good comment, not too close to what we're going to do today. As I said, in school choice, schools tend to report the priorities. How does those priorities come into place is interesting. In Northern Ireland is the only place I'm aware that they don't do that. So here, this is a copy paste from the actual guidelines from this year to get into school. If you follow the blue arrow, it says you should complete only one application. So there's only one application submitted, but then that information is sent to schools, and it works in a rather complicated way. I'm actually curious because I think I have some doubts about how, if this procedure works as well. I'm going to criticize some other procedures today. The standard procedures in which all students or all parents, because I'm going to be focusing on primary and secondary school, they send a rank. The Ulster is my top, then Stranmil is, then Queen's, then Glasgow. And also the schools are going to send a list of priorities. So Sinon has a higher priority for this school than Chris, and then Arcangelo, and then Josue. So, and then what they do in the US, in Hungary, in Paris, in many places, in whole Chile, they have all this information. Then they do some algorithm to the black box, to all this data. We do an algorithm, and then you go here, you go there, you go there. What algorithm do they use? Generally, they use one of two algorithms, both proposed by Nobel laureates in microeconomics. So these two algorithms, the general consensus is that they have different properties, but it doesn't matter which one you use. They're both going to give you something that looks the same. Today, in today's talk, we're going to review which these two algorithms, be an example, and talk about them. And I'm going to show you that these two algorithms perform really badly in two key desiderata in economics, which are efficiency and equality. I'm going after them, and I'm going after more recent research, because very recent research that I'm going to talk about has published results both using data and both using theory, saying doesn't matter. There's a ton of equivalence results nowadays, saying which algorithm they use. Any of these two or any other will give you the same results. And I'm going to show you quotes of those kind of results, and I'm going to show you that that's not true. That's what we're going to do today. What do I mean by efficient and by equality? By efficiency, I'm going to see, okay, Sinon, his preference list was first Ulster, then Queen's, then Glasgow. So he was sent to Glasgow. So I'm going to give him a 3. Where did you get in your preference list? How good? Of course, the best is 1. The worst is 100, or how many schools there are. So Chris wanted Queen's, then Ulster, and go to Ulster. So I'm going to give you a 2. And I'm going to sum that up or get the average. If the number is 1, it's perfect. We'll go to our top school or top PhD, or we'll go to Harvard, MIT, or something. That's a clear measure of efficiency, right? The number is very low. We're all getting what we really want. And it's related to other notions of efficiency like Pareto optimality, blah, blah. And the second notion where I'm going to use is equality. For example, Arcangelo, Chris, and I go to our top choice. So we have a 1. Great. But Sinon has to go to the worst school in Northern Ireland, which is in the middle of nowhere. And so your number is 100 because there are 100 schools, you go to the 100, the worst. So I'm going to look at the highest number in the distribution, which is, this case is 100 for Sinon. And then I'm going to say, well, maybe another algorithm sends Arcangelo, Chris, and me to our second choice, so we're not as happy, but sends Sinon to the third choice. So the worst person in the society is the 3. So I'm going to use these 2 numbers to compare mechanisms of what kind of distributions they tend to generate. Note that the last number, the quality, is very much related to this notion of the welfare of a society is the welfare of the worst person in the society. This Rawlsian idea that we really like and we think equality of opportunity, how should we judge an algorithm before we apply it, just like what do we expect, okay? So that's it. That's, as I said, that's the plan of the talk. I'm going to introduce these 2 algorithms in the easiest way I can think of. And then I'm going to tell you how about they are. I'm going to tell you how about they are with theory results, and then I'm going to apply it to Budapest, to the right data that we have, that you probably heard me talking about this data. And I'm going to show you how different these distributions are of rankings. Yeah, they are chocolates. They are from Sinon, but Sinon is a very generous person, so why don't you pass them to Arcangelo? Yeah, thanks, Sinon. Yeah.
So here, for efficiency, you don't consider the preference of university, right? University, sometimes they might prefer people who rank them first, but with slightly lower marks than someone with high marks, but puts them like in the bottom of their decision. So this is about.
You're absolutely right. So what Sinon said is, well, these numbers that you're comparing is only the numbers for students, right? You're not looking at the number of universities. Maybe the university is getting which high or low in their preference list. You're absolutely right. In today's talk, I'm going to focus only on students, and we will see how silly or how smart that is. But thank you for that remark, because that's what's going to be guiding the discussion today. Yeah. I'm going to say a lot about that, because you are absolutely right. Here, this talk, I'm only going to care about students. I'm not going to care about schools at all. And we're going to see that by doing that, I'm going to get better results than what's out there. But yeah, absolutely right. What schools get. So I'm going to care about where do we go in our preference list, but I'm not going to care about which student the universities get or the schools get. Maybe they get their 2nd and 7th best, or they get their 5th and 10th best. I'm going to ignore that completely. I have results for that, but yeah. So the first algorithm is called Deferred Acceptance. Yeah.
I'm gonna basically put the base investor first. So basically, if you manage based on allocate on all the base students, according to the first rule. So basically, the students get the first anyway.
Not quite. You will see it now in the example. You will see how those things are.
No, this is basically to manage the accumulate of the distribution of every group. So then the base, all the base will get the base anyway.
No, that's not going to be true. In neither of the algorithms we will see is going to be as easy as that. But you will see how the algorithm works. So the first one is called Deferred Acceptance, and by far is the most popular one. As I said, it's used everywhere in Hungary, everywhere in Chile, quite a few places in the US. It's used in Paris, it's used in England, it's used, many places. It was proposed by David Gale and Lloyd Shapley. Lloyd Shapley won the Nobel Prize for market design with Al Roth. David Gale was already dead. It was proposed in 1962 and then was really applied to school choice in a paper in the ER in 2002. How does it work? Exactly how the name suggests. So what we're going to have is the algorithm. First, I'm going to tell you what the algorithm is, and then we do the example. All the students are going to apply to their top choice. So my top choice is Strand Millis. I go and say, I want to go to Strand Millis. Perhaps Sinong is also applying to Strand Millis. It's, for now, think that each school only has one place, just to make things easier. Strand Millis gets our applications. Chris applied to Queen, so Chris is not competing with us. And Strand Millis prefers Sinong than me, so he's going to tentatively accept Sinong, but permanently reject me. That's the key. Acceptance are temporarily, but rejections are permanent. Okay, so I'm rejected. Chris is accepted to Queens. You are accepted to Glasgow because you apply there. That's the only place. Then I need to apply to my second place. So now perhaps I apply to Queens, and I'm competing with Chris. So Queens will consider the previous applications, and the new applications will reject the bad ones, and so on and so on. So let's do an example. Here we have 3 students. These are S1, S2, and S3, the blue circles. We have 3 colleges or schools, C1, C2, C3. What this means is that student 1 prefers the first block, which is college 2, then college 1, then college 3. College 1 prefers student 1, then student 3, student 2. Is this kind of clear what this represents? Perfect. So as I said, students are going to apply to their top school. So student 1 is going to apply to college 2. Student 2 is going to apply to college 1, and student 3 is going to apply to college 1. Is that clear? Why is that? They just apply to their top. So you see that college 1 now will have 2 applications. He has the application from student 3 and student 2. And as I said, he's going to temporarily accept S3 and is going to forever or permanently reject S2. So S2 now has to apply to the second best choice, which is C2. And that means C2 will now have 2 applications, S1 and S2. He had temporarily accept S1, but now he's going to reject S1 forever. And that means S1 will have to apply to his second best choice, which is C1. C1 will have 2 applications. He will reject student 3. Student 3 will now have to apply to C2. That's not good enough. He will have to apply to C3, and that's the final allocation.
So the choice from the school's perspective is irrespective of the order of their student preference. Some unidentified factors.
They have. We're assuming that they have a complete preference over the students. So let's do it again.
So, but the school is not selecting the students based on their preference.
No, it's the school is choosing according to their own preference. Yeah, yeah. The school. Yeah, let's see. So the school doesn't care where did you rank the school. It only cares about the ranking, which can be grades, interviews. So for example, here we have that student, just to clarify it, because it's a good question. So student 2 and student 3 are applying to college 1. So college 1 has 2 applications, right? That one of S2 and S3. So college 1 is going to be, according to my ranking of interviews and whatever, which one is the best one? It's going to say, well, here this represents that S3 is better than S2. So that means S2 is going to be rejected. So here, the fact that the circle appears before, it means that it has a higher ranking according to the school. Right. So it's a great question because I probably didn't explain that very well. So the rectangles appear in terms of preference. So similarly, the circles appear in terms of preference. So if S1 appears before than S3, it means that college 1 prefers S1 more than S3. So that's what determines which student gets accepted. So in the end, you're right that the school will end up with the highest ranked student that apply to them because everybody else is just rejected. Yeah. So what do we think of the allocation generated in this case? Well, it has some properties, but I'm not going to talk about them unless you want to talk about them just now. But if not, I'm just going to skip. What do you think about this allocation of students to school? Does it look good? From the school's perspective, it looks amazing, right? The schools are getting the best possible student. In terms of the students, 2 are getting the second best choice and 1 is getting the worst. So we'll see. Particularly, and this is something I'm going to get back to, this allocation is not Pareto optimal for students, because know that if S1 and S2 exchange, S1 could go to his most prepared school, S2 could go to his most prepared school, and S3 is unaffected. So we could, this allocation is okay in the sense I'm going to describe later, but it's not Pareto optimal. However, it satisfies a nice property. The property it satisfies is that no student exhibits justified envy, meaning that it can never be the case that Chris got into Queens and I didn't, and I had a higher priority at Queens than Chris. I'm not going to go into detail for that, but that's the nice thing about this algorithm. That's why it's famous. You may think, oh, it's not Pareto optimal, it's a bit silly. Yes, but this algorithm gives you something that you never get justified envy, which is a problem in real life because sometimes parents complain about why my kid didn't get there if he had a higher grades, higher scores, higher interviews. Okay, but that's the first algorithm. It's very simple, deferred acceptance. That's it. Yeah. More or less like that. Here I represented this as a sequence. You can just put in a computer and does the process of applying for you. So there's no real application. This is how the algorithm works, but you just put it in the computer and does it for you. They don't really do the applications. They just pretend this is how the algorithm is computed. What I mean by justified envy is, for example, here, S3 is not getting to college 1, but the student that is getting to college 1, S1, is the one that has the highest priority. So he cannot be envious of student 1 because the student 1 has higher priority than him. And so anyway, I'm going to go to the second algorithm, which is also very easy. This second algorithm was, yeah. I can look at what he says, probably it's just easier.
Josue, can you hear me?
I don't see anything, so yeah.
Josue? Can you hear me?
Right, maybe just write it, please, and I'll go back to you, okay? Let's do that. I'll go and explain the second procedure. The second procedure is going to be better than deferred acceptance in the sense that it's going to give us a Pareto optimal allocation all the time. But it's not that really well used in practice. It was used in New Orleans, but it was only used for a year. And then people decide, no, we don't like it. And it was also going to be used in Boston, but the educational authorities changed their mind the last minute. Also proposed by Shapley in a paper in Journal of Mathematical Economics, and then re-proposed in a paper in the AER. Oh, right, I did something. Right. So the algorithm is going to work as follows. Each student is going to apply, or if you want, think of point to the best school available for him. The school is going to point to the best available student. So I point to Queens, Queens points to Sinong, Sinong points to Ulster, Ulster points to Chris, Chris points to Warwick, and it could be like that, a sequence. This algorithm is used for many other things like kidney exchange and so on, but that's the algorithm. Let's see how it works in an example. So student 1 is going to point to the best school for him, which is college 2. College 2 is going to point to student 1, which is the best student according to the preference of the priorities of the college. Student 3 is going to point to C1, college 1. College 1 is going to point to S1. So you see, we just make the lines. This is how the lines look. Right? Just S3, there's a line going to the best college, which is C1. There's always going to be a cycle, and we find the cycle, and we assign to a student to the school they're pointing, and that's the allocation. So here, student 2 was pointing to C1, so we're going to give C1 to student 1, student 2, and student 1 is applying to college 2. We're going to assign that. And then, if a student is assigned, we remove it, and then we assign whoever is left. We repeat, but deleting these two choices that are no longer there. Okay, and that's it. So in this allocation, what do we think about it? note that it's Pareto optimal in this case. You cannot make anybody better off without harming anybody else. However, in this case, we have justified envy. Where is the case of justified envy? Can you spot it? Who is the student that is envious of somebody else and envious with reason?
That's the best one.
So he's envious of, let's see. So he could go to college 1, who is going to college 1? S2. But he has a higher priority at college 1 than S2. So you're absolutely right. That's the case of justified envy that we don't like. So these are the 2 algorithms that we have. Here, as I said, for some reason, top training cycles is kind of harder to explain. And that's perhaps why it has not been very successful. As I said, it has been tried to be used in practice, but it never really kicks in.
Is it also because
the
people making the rules tend to be the colleges, not the students, and the colleges prefer the first algorithm? They always get the regulatory regime is captured by the colleges rather than the students.
It's an interesting thought, and you're absolutely right that this TTC is better for the deferred acceptance is better for colleges, but there are other algorithms that are much better for colleges even. But it could be that, but for some reason it has not been very successful. So these are the 2 mechanisms that are often discussed, and any other mechanism that there might be around, it's just a minor modification of these 2. As I said, the main deal about DA is no justified envy. The main deal about TTC or top training cycles is Pareto optimal. Let's look at them just for final time in terms of efficiency and equality. So the efficiency for DA, we see student 1 and 2 got their second choice, and student 3 got his third. So the average is 2 + 2 + 3 divided by 3, right? Now the worst person in the society got their third, fine. Top training cycles, in this case, the average rank is 1 + 1 + 3. We divide that by 3, and the maximum rank is 3. So if you just look at the average rank, you already kind of see that TTC does better for the students here. Okay, that's fair. Right, I promise I was going to go back to Luis. Let me read his question. What is the main conclusion of the first algorithm? Is it always the case that the colleges get the best students? Okay. Yeah, I'll answer that. This is, I think it's going back to the point that Chris mentioned, that seems like in the example, deferred acceptance was doing a bit better for colleges. That's true, but I don't think that's the main key point to take. I think it could be the case. I think I don't think we know why TTC is not used in practice, but it's a reasonable alternative. But which mechanisms should we use? As I said, well, we know that they have different properties, but the answer by and large, the answer in practice is that it doesn't matter. And I'm going to show you why it doesn't matter with real data. But before that, I want to tell you what people have said about how should we choose the right mechanism. Okay, there are these 2, but there are many others. So which should we use? And this is a paper by Jean Piché from Columbia and Olivier Tercier from Paris School of Economics. And they say, the selection of which algorithm do we use probably depends on, first, that the algorithm is Pareto optimal. Second, that the mechanism yields higher utilitarian welfare, means more efficient. And third, that the mechanism gives you a much more equal distribution, which are the things I just said. Want something that is Pareto optimal, more equal and more efficient. But by and large, we have, as I said, it seems like it doesn't matter. These are data from New Orleans and from Boston. And TTC is top training cycles, DA is deferred acceptance. And if you look how many people, let's look at New Orleans, how many people are assigned to their top choice? 772 versus 762. It looks like, okay, TTC is a bit more, but only 10 people more go to their first choice. If you look at the whole distribution, it looks about the same. If you look at the number of students unassigned, 222 versus 217, it looks the same. If you look at Boston, and MTTC is matching 10 people more to their first choice. But if you think of the grand scheme of things, it really doesn't matter. Again, the number of unassigned students, 102 versus 96. So you compare those distributions, you do a test of the distributions, tells you that the distributions are the same. Again, this is not just that paper. That paper was in AR Insights last year. If you look at this other paper in theoretical economics, this is the rank distribution from New York City. In New York, students can rank 12 schools. You can order 12 schools, but not more. How many? These are DA and TTC and some other mechanisms that are not important for us. How many students are assigned to the first? About the same. How many to the second? About the same. How many to anything else? About the same. How many unassigned? About the same. So the empirical answer is that it doesn't matter. What do you do?
DA looks a bit different.
Yeah, DA looks a little bit like it's matching a bit less students to the first choice. And that is what is the answer that we found. It's not Pareto optimal, right? That's why in the top, it's not right. You're right. DA is similar, but not even less good than TTC, but about the same. But I agree, it's not quite there. But you don't see a massive difference to justify. Could we understand why that's happening? Yes, there is this paper in Theoretical Economics in 2018 that says, we find that every mechanism that is Pareto optimal, that's why DA is not there, DA is not Pareto optimal, but any other mechanism that is Pareto optimal generates the same distribution. And that's their main result. Efficient mechanisms become virtually indistinguishable in terms of payoff distribution. Payoffs are asymptotically equivalent across different mechanisms. Now I'm going to show you that that's not true. These are my first figure, and this what it shows here is I generated random data for 100 students and 100 schools. Again, each school has only one seat. And here you have how many students, the square root of how many students got placed to their first choice, their second choice, the third, the 10th choice. There are 100 schools, so the worst would be that you get assigned to the 100th school. TTC is the blue line. You see it's matching a lot of people to top school. DA is the green line. You can see that, again, it's not matching as many people to the top school. But when you look at the distribution, TTC is matching somebody to the 60th school, which is in the, there are only 100. So this means the school you really don't want to go in the lower half of your preferences. And when you look at the green line is deferred acceptance, it's matching somebody to their 25th. That's not, yeah.
In reality, these mechanisms are used to allocate students to a choice of, say, up to 10 schools. They're not being used to allocate students to up to 100.
Great point, great point. You're absolutely right. So Chris is saying this behavior here doesn't matter because the students only rank 10 schools in real life. That's what you're saying. That's true, and we're going to see how even then it matters. In this case, the students are ranking everything, and that's a great point. Maybe your critique is not real for real problems, but I still want you to look at this. This red line is the new mechanism we're proposing. It doesn't match anybody to a school worse than the 7th. The average, on average, it matches the student to a school 1.8. So it means that the average student is getting placed to a better school than their second school.
Nobel Prizes in the post.
I don't know if Nobel Prize, but I think it's, I'm really excited because of the following. The average ranking for the blue line and the green line depends on how many students and schools you have. It's very natural that more schools, the more competition, the average ranking will go down, will keep growing. it is known that the average for this n, which is a small function of n. So the logarithm grows very slowly. You put 1 million, it's like 8. You put 2 million, it's like 12. You know, it grows very slowly. The average ranking of this line, and I'm absolutely excited about this, it's always less than 2 no matter what n is. It doesn't grow with n, and we'll see why that's so important. Right.
There's another question in the chat.
All right. Can you explain how you define the efficient allocation? That's exactly what I'm going to do now. Thanks, Luis. Because what is this mechanism? I have not defined it. So this mechanism is what this mechanism is going to do is it's going to look at all possible allocations. That's a combinatorial problem. There are way too many. But it's going to find the one in which the sum is the smallest. It is not going to care at all, and this is back to your point about what schools want. It may send a very bad student to his top choice. It doesn't matter. It absolutely ignores priorities, which you may think it's really, really bad. And it sounds very bad because it could be the case that you're assigning a terrible student to Harvard and a top student to like in the middle of nowhere in Northern Ireland. But the beautiful thing is that that's never going to happen. Perhaps the top student is not going to go to Harvard, but it's going to go to MIT or Princeton. It's going to go to something better than second in theory. So that's what the algorithm does. It looks at all possible allocations and it's going to find the one that has the smallest average ranking. It's not going to care about the school's priorities. And this is perhaps why nobody has thought about this, because it sounds a very silly thing to do. Yeah, so how perhaps that figure, it's simulations of 10,000 markets. So it's definitely not a coincidence, but can you explain what's happening? Yes, I can. And to do that, I'm going to do a model. And I'm just going to describe the model in one slide. We're going to assume that students rank all schools, which is not true, as Chris said, and that's important. And perhaps that's a key problem in the model. I'm going to show that's not. But I'm going to assume students rank n schools. There are n schools, each with only one place for a student. And the schools are going to rank all possible students. Okay. And I'm going to assume that the preferences are generated randomly, and that the preference of each student are going to be independent. That's the biggest concern here. I'm going to assume that the preference of Sinon can independent from mine. They're just drawn from MATLAB, from whatever. Of course, that tends not to be true in real life. If you prefer 5A to Cinnamon, I'm likely to prefer 5A to Cinnamon as well. If you want to go to Harvard over Queens, probably I want to go to Harvard over Queens as well. But this is what I'm going to do now, and this is I'm going to do just because of simplicity, because I don't know anything, any other correlation structure I should impose. But this is what I'm.
Is this the assumption that I mean, it seems like a very logical assumption that you're making, but is this what's absent from these other people's work?
No, in the
correlated.
no, in those papers, the preferences are also independent. Yeah.
Oh, so you also
I'm,
independent in yours.
my model is exactly the same as theirs.
Okay.
Yeah, but it's a good question, because a question I'm getting is why it's different in your model. Why are you getting different results? Nothing is different in my model. That's key. The model is exactly the same. So these are my results, the theoretical ones. I'm going to explain what they mean. So the average ranking in TTC and DA is around log n. These are for very large n. So as you showed, Chris, it tends to be smaller in DA, but if you put a lot of students, they tend to be around the same, log n. But for the efficient algorithm, that number is always going to be smaller than 2. That's beautiful. Now, the maximum rank, you can show that you have n students and schools. The worst person in the society in top training cycles is going to be assigned to this 0.6 times n. So if you have 10,000 students, as we are going to have in the case of Hungary, and 10,000 schools, the worst student is going to go to the 6,000 school. It's terrible. It's absolutely horrible. Deferred acceptance does better, sending the student to log n, log n. What does that mean? Log n of, say, if you have 100 students, 100 schools, log n times log n is 21. Note that that matches very well with what we have here, around 20 something. And this is a very strange finding. Now we look at how many students have justified MB, both in the simulations and in theory. Of course, deferred acceptance, nobody has justified MB. That's what makes deferred acceptance nice. But we find that fewer people experience justified MB in deficient algorithm than in top trading cycles. Even with the fact that top trading cycles actually uses priorities, but the efficient one doesn't. Why is the intuition? Why can that be true? The secret of why people are not experiencing justified MB is because you are matching 50% to the top choice. These people have never experienced any MB whatsoever because they are assigned to the top. The people on the second choice are 20%, 25%. They only experience MB with very small probability. And everybody will always experience MB, but that's less than that 30%. So
have you tried introducing even just a weak correlation between people?
I didn't theoretically, but what I did is I put these algorithms on Hungary, which have a very high correlation, and we will see what happens. Because these results are pretty, but they have two problems. First, I'm assuming that students rank everything, the problem that you say. The second problem is that there's no correlation. If I can convince people that these are not real problems and that the efficient algorithm still works nicely without these two assumptions, I have a case. Otherwise, I don't. So the second part of the paper is just using data to prove you that I have a point.
So you can't do that theoretically. There's more something you do in theory.
I can probably do it, but I don't know what's the right way of doing it. But I can do it. I just haven't done it. Yeah. But that's yeah. So now I'm going to use the data. The data is from the assignment of secondary school kids to Budapest. We have in 2015. This is data we got from the Education Authority. We have 10,000 students applying to 250 colleges, or they are assigned when they are 14 years old. The secondary school is whatever you expect. Priorities are based on interviews, grades, the standardized tests, and we have the two real problems. There's a strong correlation, and students on average only rank 4 schools. So we have that problem. The preference lists are very short. And furthermore, we have another problem, that is that schools don't rank all the students. The schools only rank students that apply to that school. So if Arcangelo and Chris apply to Queens and we don't, Queens is only going to tell me what's the ranking of Arcangelo and Chris, but it's not going to tell me what's the ranking for the two of us. Okay, so what do we get with this? As I said, I'm going to show you results with the real preferences that we get and with the preferences that I construct using the small preferences. So with the real preference, I only know what Arcangelo and Chris ranking comparison between them, but I'm also going to construct the large preferences in which I'm going to add Sinon and I. I'm going to do that with standard techniques of data augmentation, but you don't need to believe that. So this is what I get with the full preference list in which students rank everything. This is not the real one. I constructed this. The efficient algorithm on average is 2.6, less than 3. The average student than 3. Nobody's assigned to something worse than 16. TTC ranks somebody to 240, DA somebody to 235. So this figure shows that correlation doesn't matter. DA and TTC still perform garbage with correlation. What I haven't shown you yet is what happens with short lists, in which people don't rank 250, but just rank a few. This is the next figure. The student that ranks the most number of colleges is 14, Nobody ranks more than 14. That's the guy who, is quite desperate and just playing safe. But most people only rank 4. Here you see that the worst student is sent to his 6th choice on the efficient algorithm. The worst student in DA is sent to the 13. The worst student on TTC is sent to the 14.
So the incentive if you're in a CTC or DA regime here is not to fill in all your preferences. Fill in the first 3.
Say that again. Sorry, I didn't catch it, to be honest.
Why would you fill in all 14?
No, so somebody does that.
But why? What's the incentive if that may result in you getting?
Because if you don't feel enough, you might be unassigned, and then there. Yeah. It's not here. I should have another bar for unassigned. They all generate the same number of unassigned. They all generate, but that's why. Same problem in Northern Ireland. For example, somebody in Bangor just ranked 4 schools, didn't get into any, was assigned to something in Newton Arts. Either you are unassigned or you are assigned randomly. But this last figure shows you that correlation is not a problem, and also small preference lists are not a problem. You still get much smaller average and maximum. And if you want the summary statistics, they're in this table. The small one is this is the one with the real preferences, the last one. Average ranking of the efficient one, 1.5 versus 1.9 and 2.1. You may think it's not a lot because here it's just smaller, but still something.
Justified MB though.
Justified MB, exactly. Now the justified MB has reverted about the same. 46 versus 44. This is the only prediction that we don't see. That actually depends on correlation. It's still interesting because remember, this is not using priorities at all. But you're right. This is the only thing that it's in theory, but not in the data. What are we going to do to check if this is robust? We're trying to get the data from New York that they use in AR Insights to test whether this is just because of the structure of data or this is always the case. But this we see exactly what theory predicted. Here we don't. So that's really just to conclude. Is what you already pointed out.
Could you
Yeah.
use subsets of the data?
Yeah. It's every time you use subsets, it becomes tricky because you need to eliminate seats from the schools. Even now, we're just using the subset of Budapest. But to do that, we have to eliminate people that are applying outside Budapest and taking a seat. But it's a good idea. Many people are now using robustness in subsets. I haven't done that. What I'm trying to do more is get it in other data to check. But it's a good suggestion. So in theory and practice, the efficient mechanism is much more efficient. Not surprisingly, well, somewhat, because people didn't think that was the case. The efficient mechanism is much more egalitarian. In theory, that we see in theory and practice under many conditions. In theory only, we see that the efficient mechanism generates less justified MB. We don't see that in practice, but it's interesting. We think that that means that there is real potential for applications of this in practice. How much time do I have? Perfect. Well, I'm going to end very fast, but I don't want to give you an idea that this is like without any problems. There are 2 problems for this efficient mechanism. So the first one is that it completely ignores priorities. I think when we submit this, that's going to be something we need to address. Yeah.
I think that in the country there might be a ranking for all these schools, like the university rankings for
Yeah.
Rather than assuming that people have independent preferences, rather people are all following that university
Right.
So this might be a way that you can test the efficiency of your But
Isn't that already, if there was a ranking, that would already be, because using your data, you actually have correlated preferences, right? So maybe the rankings are informing those preferences already. It's already inbuilt.
So I'll just answer the question. It has an easy answer. So you're right that in some cases, everybody would have the same preference. So for example, they ask us how much money do you want to be paid? I mean, the more the better, right? Or in some other cases, it is the schools that have the same preferences because their priorities is defined on a centralized exam. Say in Paris, to get admitted to one of the polytechnics, they all use the same exam that we all take at the same time, or the GRE for PhD admissions thing. That's something we could look at, but it's well known that if one side of the market, students or schools, they all have the same preferences, whatever mechanism you use to assign is going to give you the same. That's a result. It's a null result. Basically, it means that if, yeah, just take it as a given. Whenever one side has, everybody agrees, the mechanism doesn't do anything. They all give you the same. So that's the short answer. It's a good idea because actually it happens in practice that everybody, all the schools base their ranking on some exam. It happens, but in that case, all algorithms are the same. The correlation index is 1. Yeah. Just to say it like that. So as I said, I was going back to the 2 problems of this. I want to run this past you to see if these answers are convincing. The first one is, we don't worry about priorities. As I shown, that doesn't matter. People are still assigned to something very high. Something we don't have results is for the variance, but the variance of this algorithm is very small, showing that everybody gets something around 1 second, 3 or 4. The most complicated problem is the following. Some algorithms can be manipulated and some can't. What do I mean by manipulating? It means that my real preference is that Strand-Millis is my top choice, then Glasgow, then Warwick. But perhaps I think that if I lie and say that Warwick is actually my top choice, I will increase my chances of getting to the school I really want. You can show theoretically that that will never happen in top training cycles or in deferred acceptance. But in the diffusion mechanism, that's not true. You can actually manipulate it. I'm going to show you an example. This is the same example we had before, but I added another student and another school just to make it more interesting. If you compute the efficient mechanism here, I can give that to you, but you can assign S1 to C2 and S4 to C4, and then S2 or S3 to C1, and the other one will have to go to C3. So this is the efficient allocation. You can check that the sum of rankings is 1, 1, 1, and 2, that's a 5. But look at S3. If S3 had perfect information about what's going on, could he tell a lie about his real ranking to get a better allocation? He can. Let's see if you can spot what is the lie. Can anybody see what do I need to say if I'm S3 to get something better than C3? Can you tell how can I manipulate this algorithm? Maybe it's not so obvious, but no, it's not that clear, I think, but it is possible.
Oh, someone in the chat has an answer, I think.
Oh, really? What was that?
Which state for state 3?
Yes, exactly. That's the way to do it. So instead of saying that C3 is your second choice, you send it all the way to the back. Why? Because now this allocation has ranking 1, 1, 1, 4. So that's very high. That's 7. So if instead we do this new allocation has ranking 1, 1, 3, 6. So it's less. So you end up with C1 rather than C3.
And actually, this is everyone's worse.
Not a Pareto improvement. Not a Pareto improvement because S2 is worse off. Right. So here you are harming S2 at the cost of improving S3. But this shows that the mechanism can be manipulated. Whether we expect this to happen in practice, I don't know, because it's very risky, right? You're sending your the choice that you're going to get all the way down your preference list. But it is. So it can be manipulated. Yes. I think what I'm trying to do in the paper is not to argue that that cannot happen, which there are some results. There is only one paper that has looked at this efficient algorithm came from Penn State that showed that under certain conditions, you should not manipulate it. I don't want to argue that. What I want to argue, yeah.
Whenever these algorithms are used, do the applicants actually know what the algorithm is?
No, you don't.
No.
You know what the algorithm is, you do, but you don't know you need to know the preference of everybody else and of the schools.
But do you really think they know the algorithm?
Well, yeah, the parents know. The education authority spends a lot of money telling.
I mean, you say they know, but we've sat through a whole seminar to understand how it works. I mean, I think
Yeah. No, probably they don't. They know the name, but
they know the name, but they don't really know how it works.
and we see a lot of
Black
mistakes. Yeah, exactly. So that's what I want to come back to. There's a lot of recent papers that document that in algorithms where you should not lie, that it's never going to give you a better outcome, people always lie still. Not always, but very commonly. This paper in the AER, the mechanism is truthful. Why aren't you? A lot of other papers that document this thing. And a recent paper in experimental economics this year that shows that they do this in an experiment. They compare DA versus TTC, and they find a lot of lies. Only 14% or to 30 are actually people telling the truth in an experiment. So my point is not that, okay, yeah, people could manipulate this and could affect the results, but people are doing that in any other mechanism. So why do we care? And there is very strong feeling for this. Different line of research would be to do exactly what this guy did, compare DA and TTC in the lab, but compare it against the efficient mechanism. As Chris says, it's really hard to know what the efficient mechanism is, even harder to think, how can I manipulate it? So my feeling is that manipulation is not something theoretical, but something related to how complex it is for me to understand the norm. And we don't really have any measure for that in game theory or anything. Right. So to conclude, just this paper I want to mention, TTC, as I said, has not been used in practice. People have been trying to understand why not. There's a recent paper in the AR Insights, the Nobel laureate and that says, well, let's try to revive TTC. So what they just recently show is that among all mechanisms or all algorithms that are Pareto optimal and non-manipulable, there's no mechanism that just generates fewer cases of envy than top trading cycles. Our mechanism is not Pareto optimal, so it's not there. It is Pareto optimal, sorry, it's manipulable, so it's not in that class of things. But our mechanism generates less justified envy in theory and about the same in practice. So, yeah, I'll finish there. I don't want to talk too much about this. Things to do some experiments, check if the distribution is robust, and apply this into real life. And that's it. Thank you very much. That's it.
So your last point there,
Yeah.
go back.
Yeah.
No, next slide. And the very last slide.
Oh, the very last slide.
The last point.
Yeah.
Right. So this one, try to apply this in Northern Ireland.
Yeah.
We should try and set up some sort of meeting with whoever's responsible.
We should, and I think because
we need to figure out what exactly they do here, and whether it's even on their radar that other options are available. It might be worth considering. What point do you want to do that? Because this is something that could really have an impact, no?
Yeah, I think that's true. I mean, much of the applications of DA in real life were carried out by academics. So I am aware that This started with Alrod going to places and say, look, we need to do deferred acceptance. Chile happened because some economists went there and told them. And I think, as you said, there's scope to do this in practice. Particularly because you were asking me, do parents know what is happening, what the algorithm is? And I don't think we know what the algorithm is, the one that North Carolina Education Authority is using, because he's sending everything, they're sending everything to the schools. But I have a very strong prior, and the order in which people reply determines the allocation. So
Maybe we should also approach the School of Education here and some of their academics who really have the local knowledge about the school system.
Yeah.
And can open doors to speak to people.
Yeah, I already did that. That's somebody called Gallagher, I forgot his first name, who wrote a report for the Education Authority saying like, oh, this is how schools.
Previous Provost Chancellor, I think.
Oh, really?
Yeah, as well, yeah. Okay, that's a great idea. What point do you want to do that? After you publish this or now already?
I'm meeting him next week.
Irish data in your paper?
I mean, I'm problem dreaming, but I'm trying to pitch that to AER Insights. So I don't want to make that bigger. Whether it's going to work, probably not, but probably getting more data would be a good idea. You're right. I think there is potential to do this. So my co-author is using it now for allocating the seminars in the University of Mannheim.
Allocating seminars?
Yeah. So think of it as graduate classes. So they call them seminars. They have a lot of demand, some courses. And in that case, you can think that priorities of seminars of students don't matter. So they are doing there. Look at data, the only place where this mechanism has been applied is to allocate teachers that have just graduated to schools or placement schools. So that's the only thing I'm aware. But
the nice thing about this is, could you sell a narrative that it would also help combat school segregation? That's the problem in Northern Ireland.
Yes, because here exactly, schools cannot say, I prefer this student over this student. Yes, I think that's a good selling point.
Yeah, so that's something we could go to Gallagher with.
Yeah, I'm meeting him next week.
He's interested in,
right.
I think.
I didn't know.
Yeah, he wants to have more integrated schools. And that kind of thing.
I think he told me he's semi-retired now. But...
Yeah, I think he's given up on admin, but this is the sort of thing that he would be interested in.
Yeah.
Is there more questions in the chat?
Let's check the questions. Next, I have one concern. Wouldn't this affect incentives to study in the first place? Let me think what that means.
Well, not if it's compulsory.
Well, I don't see how. I mean, you are getting assigned to a school you prefer more. I don't really see what the problem is there. Why does that affect the incentive to study in the beginning? I don't see. Maybe you want to write more, because at the moment I don't really understand what the question is. If anything, should incentive it in the first place, because I also was reading the Belfast Telegraph and I read that somebody listed 4 schools was not placed, and the mom said like, yeah, I'm not going to take you to Newton Arts, I'm going to homeschool you. But if you're going to have a higher chance of going to a school you wanted, it should give you more incentives to actually participate in the mechanism. The best students do not have an edge, so why student? Yeah, okay, so it's back to the role of priorities. As you said, the best students are not going to be assigned to the top school for sure, but we're going to assign them to a top 1 or 2 schools. So it's not like they're having a massive drawback. And so the distribution is very highly concentrated across the 4 top schools. So we're not sending any future Nobel laureate or Fields Medal winner or Pulitzer Prize winner. We're not sending any of these guys to a school they really don't want to go. We're sending them to, and if you look, actually, this is a point I haven't emphasized, but in the literature of education and econometrics, they find that the students, if you send the top guy to any other school, these guys are going to excel anywhere. The real effects are on students, that the ones that were doing the busing in the segregation programs before. The guys you are sending them to a better school, they really have a strong benefits. I don't want to mix the paper with this literature, but even reinforces the point that the top student is going to excel anywhere. Yeah, yeah. Yeah, exactly. Yeah. Yeah. Yeah, I mean, you're absolutely right. I mean, this by construction, if you look at the segregation index of the allocation, it's 0. Because the placement is not determined by anything else but by preferences, and everybody has an equal shot, not affected by whatever they did in the past. You can call that fair, you can call it unfair, but it's just a different axiom, I think. And only doing this in real life, we will be able to see. Of course, it would be interesting to compare two systems and see the effects on educational attainment, wages, but that's, first we need to run this and just check what is the distribution of the ranks and then everything else. Yeah.
So mixing these mechanisms would people more like choose talent, because we know that in computer science, in order to increase the security, so they mix different mechanisms, so that people don't know which mechanisms they are using. So,
yeah.
So is this like there's any possibility here, like we can mix EA and this mechanism so that efficiency of all the matching cells?
You could do something like that. Not in the lab, because they would call it deception, but in real life, yeah, it's harder to be able to do it. But in general, you could do a lottery over two mechanisms. Say, give us your preferences, and we might do the A or we might do the fission. And people, yeah, may be less likely to lie. But I have a deeper concern. My concern is more, as I said to Chris, that people don't understand what's going on. And if it's strategy proof or if it's not, people are going to rank something. And all papers find that people lie. Why? We don't know. People lie even in very basic situations. This paper in games and economic behavior, they ask students to this school choice, but about where do they want to do their placements. And some placements is the same, but comes with a scholarship. So it's going to Queens without scholarship or going to Queens with scholarship. And they say, well, we can agree that you want to go with scholarship, but they find a lot of people that rank those things differently, which makes, little sense in that context. There's a lot of evidence of that. For example, in these truthful mechanisms, like the one they use in Hungary, it's never harmful to you to rank 10 schools, or to rank, you should rank as many as possible. That's never going to harm you, but people don't do it. Why? We see evidence of this, but yeah. Anyway, thanks a lot, and let's have a beer.
Yeah, let's go to the pub.
Yeah, let's head to the pub.
Which one we go to?
Whichever you want.
Where
The practitioner?
yeah, why
Yeah,
not?
yeah, I like it.